Welcome to Alchemy Wizard. I'm Tom. Let's get to it. Now, I just want to say that the penny video is doing phenomenal. I want to have more stuff like that for you guys in 2024. So I'm working together with my chemist to see if we can come up with some stuff like that. But we don't want to neglect those of you following the other progress with the colloidals and things like that. Today I want to talk about the laser ablation project. As you know, I did a couple shorts on this, and then I did a longer video showing you how we took magnesium rod and we created a colloidal from it. Well, we had some unexpected results from this, which has branched this off in a new direction. So I want to share it with you. It's still all experimental, okay? We're in a field where anything goes. You know, my chemist and I were quite shocked at what we found. But first, a little background. Magnesium is really hard to turn into a colloidal. I have plasma arc and low voltage electrolysis method, and both methods do not work. The low voltage electrolysis method will create a very low yield colloidal, maybe 8 parts per million, but it'll only last a week or two, or maybe even not even 2 weeks, maybe 3 if you're lucky, and the colloidals are all gone. It just disintegrates into ionic content. The plasma arc will not even create colloidals. It just melts the material and it turns into an ionic, and never, for whatever reason, it never turns into a colloidal. So when I started looking into laser ablation and I'm looking at the metals that I want to use, magnesium was a very promising one because A, it doesn't work very well with either of those methods, so maybe it will work well with this. And B, it has a very low melting point. And my theory was, with a nice low melting point, if we focus these 4 lasers, and I will put links to the shorts and the previous video where I talk about this if you want more information. We took the 4 lasers and focused it on a spot on this. We'd have enough heat because of the melting point of magnesium to melt the magnesium off and create a colloidal. Now, how that typically is supposed to work is you got the heat of the laser in a spot on the metal. It vaporizes the metal. So the metal removes because of the intense heat, the metal removes itself in very tiny particles. And then it hits the water, and the water cools those particles down, and it instantly changes those particles into a colloidal when they cool down, which is a neutral charged thing. Now, the metal on here is all neutrally charged. And when you remove the metal from here, and it goes into the solution as an ion, it's not neutrally charged anymore. And then we need to recombine the 2 electrons once it's free of the metal to create a neutral charged particle. Basically, we got little tiny bits of metal floating around. It's called the colloidal. They start then grouping together, and they form larger particles because this thing called van der Waals forces, which is a quantum thing. When a particle is neutral, it will start to attract other neutral particles to itself, and then it comes together in nanoparticle size, anywhere from 1 to 100 nanometers, depending on the properties of the metal and the conditions. And you have a colloidal, a neutrally charged particle suspended in the water, not dissolved at all, just suspended. And nanoparticles are large compared to ionic particles, which are extremely tiny and are dissolved, in other words, bound to the fluid. So that's the idea of a colloidal. Now, my theory here was we heat the magnesium up, and it has a nice low melting temperature, and we create a colloidal out of it. Was it going to last? I don't know. I mean, it could have. My thing was maybe this process will have something different and be able to create the colloidal particles, where my other 2 processes don't. That was my theory. The other thing was magnesium is a nice soft metal, and I wanted to see if we could actually get material off here by focusing the 4 lasers in a particular spot. Well, it did work, as I showed you, and I'll show you the final thing after I was done. Shows when we started with distilled water, and then after a certain, I think 20 minutes, I got the picture up there, but I don't remember it offhand. And then 20 minutes we had, I think, like 3 parts per million colloidals, and then we had 5 parts per million colloidals. And I touted that as a pretty good success story. And, I even showed pictures of where the laser had bored a hole in the magnesium. So, I figured, well, it's a success story. Christmas was coming, the holidays. So, I took the water and I put it in what I'm calling sample 1 over here. And forgot about it. What I wanted to do was go back and test it in a week or so and see if we still had colloidals. Because the whole point of the laser thing, besides seeing if it can be done, was to see if I could create a stable magnesium colloidal out of it. So if my little 5 parts per million magnesium was down to 0 parts per million in a week, well, it's great we were able to create a colloidal with the laser, but I didn't achieve my goal of creating a stable magnesium colloidal. Well, holidays came and went. It was probably about a week or 2 before I got to dumping the sample in, which was Monday, dumping the sample in the microscope to see what it looked like, and OMG was I shocked. Here's a picture of what I saw. This is sample 1. Now, when I finished this, when I put the stuff in here, we had at best a 5 parts per million solution. Now, what I'm looking at in the microscope here is at least almost a 20 parts per million solution. We created more colloidals over time. Now, there's only 2 explanations for that. One is something is happening that we don't understand. Or 2, the sample was contaminated. Maybe there was something in the container. I use these containers for lots of things, although I'm pretty sure this was a brand new container straight out of the box. Can't say for certain. But it's possible I had a colloidal in there and I didn't wash the container very good, so it mixed up. So that's possible. So that brought me this week to sample 2. Now I was very careful with sample 2, doing a lot of more, taking it a little bit more slowly than I did with sample 1. Sample 1 was just, hey, let's just see if this is going to work, Sample 2's now, we need to replicate this process and see exactly what's going on here. So, this was sample 2. This is my rig here. This shield prevents the blinding green light from getting all over the room and injuring eyes that aren't protected. So I did sample 2. I was very careful about sample 2. I measured the weight before and the weight after. Sample 2, after much work, now you want to understand something. These lasers only work for about 10 minutes and then the batteries go dead. And not only that, they're not full-time lasers. You really can't run them for a half hour or 40 minutes. Their laser pointers will burn them out. So it's not an easy process to bombard this stuff, this fluid, with the lasers. It takes time. So it's bombarded with the laser for 10 minutes, recharge the laser batteries, which takes a half hour, and bombard it again for another 10 minutes to try and get up to about 40 minutes or so. This sample I took to about 60 or 70 minutes. I've since ordered some leads for these lasers so that I can keep them plugged in. So at least I don't have to recharge them. I'm still going to have to run them for 10 minutes and then stop so I don't burn the lasers out, let them cool down for a few minutes and then run them for another 10 minutes. But at least I won't have 40 minutes in between waiting for the laser pointer batteries to recharge. So that's going to help my future research on this because I need to do future research on this. So sample 2, I'm goading you guys along with sample 2. Sample 2 was similar to sample 1. I added 8 or 10 parts per million. I cooked it a little further, so I actually had almost a 12 parts per million solution of colloidal material in here before I stopped the laser ablation project. Then I let it sit for a day, 2 days. And you want to know something? The colloidal content continues to go up. Now this is after 72 hours. Here's a picture of 72 hours. I'll also show you some of the pictures of as the days progressed. 24, 48, 72. You'll see the colloidal content is increasing and nothing is happening. We are not applying a laser. We are not applying electricity. All we did was the initial laser ablation technique, which gave me 8 or 10 parts per million colloidal, and then let it sit. Something is happening here. And that's going to be my investigation in this week. Uncover what's happening here. Now, I had extensive talks with my chemist on this, and we think we understand what's happening. And it's actually connected to the penny video. In the penny video, we take our filings, zinc filings, and we put it in the beaker, and we heat the beaker up with fluid. We also put zinc chloride in there, which is just zinc and chloride bound together, just so that you can make a dissolvable form of zinc. So we have zinc ions floating around in the water when we do the penny thing. And that gets attracted to the penny, and the zinc deposits itself on top of the penny surface. Now, when the zinc is depleted from the zinc chloride solution, the filings in the bottom have to give up their zinc to fill the holes in the solution. They have to, they must, it's a chemistry thing. And so the zinc is replenished from the filings in the solution. It becomes an ionic zinc again. And the process continues, and that's why we can just continually make a whole bunch of these gold pennies. Well, we believe something similar is happening here. Me and my chemists think it has nothing to do with the heat that is causing the process here. And I've done some tests to decrease the focus. I've done what I call a refracted test, and here's a picture of a refracted test. You'll see the light is refracted all over the inside of the beaker, and it's not as concentrated. What I've done is taken the laser light and refracted it all over the place. So it covers a wider area of this thing, but it's not as hot. Technically, it shouldn't be hot enough to melt the solution. But you know what happened? The zinc still came off of here. Why did that happen? And this is where it's connected to the penny idea. My chemist and I believe that the laser light is extremely energetic. There's a lot of energetic energy in the light, the photon light. And it's bombarding the zinc with this energy, and the outer electron. I know this is going to get geeky, guys, so if you don't want to listen to the geek thing, just kind of hold your ears a little bit, all right? Because some of you people might be interested in the geek end of this story. So the laser light floods over this thing, and it is so intense, not in heat, but in light energy, photon energy, that it excites the metal to give off the outermost electrons. The 2 electrons in the outermost orbit gain so much energy from the light photons that they separate from the magnesium. When that happens, that magnesium atom removes itself from the magnesium rod. In essence, we've created magnesium ion, like we did with the penny video, except that we used zinc chloride there. So we created a solution with magnesium ions in it. And that doesn't give us the colloidals. But here's the thing. Somehow, these ions are now turning into colloidals over time, even after we remove the laser light. So why? Well, we believe that there is a tremendous, in the normal colloidal process, we either use low voltage DC or we use high voltage plasma arc electricity to flood the material with electrons, which then removes the material. Kind of like what this is doing. All right, but we're using electricity, and we have an anode and a cathode. So we're dumping in electrons, and then we're taking electrons out. Now, it's a constant source of electrons going in and out and in and out and in and out, right? So now we remove the source, the energy source, and the only thing we have left in the solution is whatever free electrons happen to be floating around in the water, which probably isn't a whole lot. But with the laser light, these electrons have no place to go. We're not taking electrons out of the water. We have no anode or cathode. The electrons go into the solution, become ionized particles in the solution. And so now we've removed the material here because of the laser light. We have ionic magnesium floating around in here. Now we removed the laser light, but we haven't removed the electrons, the free-flowing electrons that have no place to go anymore. They're still in the liquid looking for some place to go. Where can they go? They can't go on here because this is neutral charged. But these ions magnesium ions that are floating around in here are not neutrally charged. They need those electrons, because we removed them, in order to be happy. So those electrons that are floating around in the water now start to find these ions. They fill the holes, the two missing electron holes, and guess what? It becomes an ultra tiny piece of colloidal. And then this keeps happening, and these colloidals start combining together because of van der Waals forces, which is like a magnetic attractive force that we don't fully understand. And they start clumping together to create nanoparticles between 1 and 100 nanometers. And over time, the ionic solution that we've created in here becomes colloidal. And we think that's what's happening. And furthermore, we think we can do this with other metals. I'm going to try the zinc. I have a whole bag of zinc filings. I'm going to put some zinc filings in the bottom of this beaker, and I'm going to see if we can create a stable colloidal zinc using this same method. Colloidal zinc and colloidal magnesium and zinc share very similar properties, my chemist says, and so, in theory, we should be able to create zinc colloidals the same way that we're doing the magnesium colloidals. And that'll further verify what's going on here with our magnesium. It's fairly exciting stuff, and we don't fully understand it, but, it's experimental, so the whole thing could fall apart tomorrow or something like that. But that's what I'm working on. And I'm going to have some other videos this week. We'll see what happens. Now, I know this is a kind of a long video and a geeky video, and, for those of you that weren't into the geeky side of things, well, we'll have some more fun videos for you. For those of you who are really interested in cutting-edge kind of stuff, this video will definitely reaches the edge of cutting-edge understanding on colloidals and exciting materials with laser light. So, I'm Tom, Alchemy Wizard. I'll talk to you guys again soon. Have a great 2024. Let's hope it's fantastic for all of us and we create wonderful alchemical stuff in our lives. And oh my God, take 2 cools for reaching the end of this video. You certainly deserve it.